My name is Halal Rashid. This presentation, I will talk about the next generation of phase array simulations in HFSS. Agenda is as follows. I will present a phase array design workflow. In that workflow, we will talk about element design. We'll talk about the phase array synthesis and analysis. I will talk about the install performance. Key takeaway here is that I will show 4 examples of complex 3D component array simulations. These arrays consist of 64 elements all the way up to 88 elements. I will present post-processing capabilities as beam steering, field visualization, and coupling data. Simulations took less than 6 hours. This includes adaptive meshing and the frequency sweep, and this is obviously all full wave simulations. Design workflow for 5G array could look something like this. So where you start off by designing the antenna element and then designing the phase array. And the next step would be that we are looking how this phase array would look like if we, the properties, how it would be if you put it into a casing. How would that affect the radiation patterns, for example? And if we take that casing and we put it on the mast, what would be the install performance? And we can take this radiation pattern and we can use them in SPR plus, and we can use them in EMIT to look, for example, at link margin, RF interference, EMI, and we can look at beam forming, coverage estimates. This way together, we are developing specifications that help to improve the phase array and the radio unit. When this is done, we could go on and look what is at the network planning and coverage studies. For example, what is the coupling between the base station UE, as the animation show here that we have a base station on a tower, how the rays they propagate, and if we put the UE here, what would be the coupling? We can further do analysis where we have several base stations, what would be the handoff if you have a UE somewhere there. And obviously for these radio units, multiphysics becomes an important part of it, because what happens to radiation pattern if you are increasing temperature? What is happening to your mechanical structures when you're increasing temperature? Do you have deformation? And then if you do have deformation, how would that affect your radiation properties? This could all be simulated, the integrated workflow within Ansys suite. But today I'm going to focus only on these 2 parts, and mainly on the antenna synthesis and analysis. So we may have different approach depending on what we are looking at. So if we are designing really large antenna arrays, so large that they can be considered infinite arrays. So how large it needs to be? So it could be, for example, 40 by 40 antenna array elements. In this case, we could say that the edge effects, they could be ignored compared to the rest of the array structure. And in this case, we could simulate it by using one antenna element in an infinite array environment. It would be that it has the same coupling in all directions. This technique requires low computational resources, is really effective when we have large structures. However, we can still use this technique to design a finite array element. Once this element is done, then we can bring it into the finite array and do the finite array analysis. And there is 2 approaches here. First approach would obviously be the brute force approach, the explicit, so where we can draw the complex geometry and we can have the fewest assumption in that complex geometry, right? And then we do adaptive meshing, solve. This would include all edge effects, all edge treatment, mutual couplings, arbitrary excitation, everything would be included here. This is full wave analysis. Another approach would be that, as we can see, for example, in a picture here, that if we have some radiators here, we have radon and other things, we can break it down to different 3D components. So we can represent this whole antenna with a few 3D components, right? These 3D components, they are edge conformal mesh interface between each 3D components. So basically from one neighborhood to the other neighbor, have edge conformal meshing. They have the ability to adapt component mesh independently. So if you have 5 components, each 5 components are using adaptive mesh independently, and the entire array now. So using these components, we are constructing the entire array, and we are making a global mesh. So the entire array is analyzed. It means that we have all the edge effects and edge treatments included. We have mutual coupling. We have arbitrary excitations, exactly like the explicit, but this is very efficient way of doing that simulation. And this also uses the domain decomposition method to distribute compute resources. So if we begin, we look at the array element design for the unit cell here. So we're at the infinite array here. So what we need is that here in the first part, we can see an antenna element. This is a cavity backpatch antenna. We see the 2 ground planes and the vias connecting them to create the cavity. We have the patch antenna here. And in an infinite array, we may use the lattice pair here. This is the periodic boundary conditions. And inside this unit cell, we may add, if we would like to, a radome as well, and have it included in the analysis. Once we have this design ready, we can start doing analysis. We can use, for example, design of experiment to obtain response surfaces, to optimize on that response surface. We can use that to do tolerance analysis, and to look at the sensitivities of which variables should be in a full optimization scheme, for example. This is really good way to figure this out. And we can also look at the array factor, right? So for example, if we have this 8x8 array factor, we could see at least what to expect. Okay, what is the gain? What is to expect? So some expectation. So we could also look, for sky blindness, for example. Next picture below shows the active S parameter. This active S parameters is for different beam steering angles. We can see how the active parameters are changing for different beam steering angles. And forgot to say, the picture above here is that we are seeing the azimuth cut for different beam steering angles again. So another approach what we could have here is that if we would have designed this antenna without the radome, we could use the Floquet port, the Floquet technique to do an investigation of initial radome material selection. What I mean is that basically we could put a Floquet port in the bottom and the top, so incidence and output, and we could put our radome structure in between here. We look at the reflection coefficients versus angle of incidence. This is the reflection coefficients which we'd like to minimize in such a way so that when you put your radome on top, that it's almost invisible to the array itself. So going now to constructing the 3D component array, we use a full wave analysis of a true antenna array geometry, including radome. So here we are using 3D components, the domain decomposition simulation technique. This, as I was saying, this makes use of that we can create the entire array using a few 3D components. As I was also saying that these 3D components, they have the ability to mesh independently and also in parallel. So we can see that we can, if we have this antenna array, we have the cavity packed patch antennas here, we have extended ground, and then we have the bending of the radome, and then we have further ground here. This picture from side view, we can see how the radome is bending down. Okay, so this 3D component would now consist of the cavity patch, back patch antenna, and we simulate this structure, and we can populate this entire array, the 8x8, since we are only having this same element here. If we would have different elements, that would be no issue. Then we could represent it with a different 3D component, and it does not need to be periodic. We could place them anywhere. And here we can see the meshed corner elements of the radome side. So really with 5 3D components, we are able to make the entire structure and also get the global mesh and simulate that. So here's the example of the 8x8 array for 28 gigahertz, and this has a radome that covers all the radiators. It's bended, as I was showing. You have extended ground planes. This is full wave simulation with adaptive meshing and also frequency sweep included. On a 40 core machine, it took approximately 1.5 hours. What we could do that, so we can start doing analysis on array level. For example, if we look at case 1, where we have some ground structure, extended ground here, this is the same size of the antenna element. And in case 2, we have 2 of these. So this is twice as long ground as we have in the case 1. This is quite similar, and they also took about the same time to simulate. So firstly, what we can look at is, for example, the return loss. We have plotted the return loss for 2 scenarios. So one is that is the corner element, and the second is an element further in. The red lines are representing the antenna with this ground, and the blue is with the twice as large ground structure. And we can see that there is a significant difference between having twice as large ground, extended ground, compared to this one. And if we look at the radiation pattern, so if we excite all elements and we look at the total gain with a beam steering of 20 degrees, they are fairly similar. If we look with 50-degree beam steering, we see that there is some difference in the side lobe levels. And here's a plot where we're doing the beam steering in the azimuth direction, and this is post-processing, really. So we are not re-simulating for each beam steering angle. This is only one simulation, and in this simulation, we have the post-processing capability to beam steer it to any angle without need to re-simulate. Okay. This animation shows the wave propagation inside the array. In this case, we have excited only the corner element, and you can see how the wave is propagating and how it is coupled to the neighboring elements. This example will show again the cavity backpatch antenna for 28 gigahertz. Difference is that we have 8 panels of this 8x8 radiators, and they are separated each panel by a ground piece of ground structure here, and they're all covered with the radome. Again, you have the bended radome. If we look at the corner element, we can see how it looks like, and this structure has approximately 13,000 vias. This is a full wave simulation you're seeing with adaptive meshing included on 128 core machine, we are seeing that this takes about 2 hours to simulate. And then the question could be like, how does this compare to the explicit simulation? Well, if we look at that picture, it is in excellent agreement with the explicit solution, only that it just takes about 2 hours. This design is a 4x8 array for 3.5 gigahertz. It consists of 32 subarrays. You can see in each subarray we have 3 radiators. This radiator consists of stack patch antennas. We have the power divider, we have the routing, we have also in here the calibration network. So we can see that there is quite a complex structure. It's actually a very complex structure. We're using again the 3D component array technique here. So we used 128 cores on Ansys Cloud. This took for a full wave simulation, including adaptive meshing and frequency sweep. It took less than 2 hours. This is really impressive. And this has 160 excitations. We have to remind ourselves that also there is excitations for the calibration networks. So looking at post-processing, once the simulation is finished, we have the access to all antenna parameters. We have access to S parameter, active S parameters. Figures here show the frequency, the peak gain versus frequency. The red corresponds to the IEEE peak gain, and the blue is the realized peak gain. The second plot here we are seeing is the active S parameters for different beam steering angles. And again, so this is only one simulation carried out. The rest is post-processing. Furthermore, we can look at coupling, for example. So if we, in this picture, what we are seeing a corner element, the return loss of the corner element, but also the coupling to nearest neighbor and next nearest neighbor of the corner elements. And we can also look at the coupling data between all elements through color coding and mapping. So this is a really easy way to just have a first glance on how it looks like, and then go into depth to make such plots and see how it looks like. Furthermore, we can, since this is full wave simulations, we can take this dual polarized antenna as I just showed, and we can excite them really as we wish. We can excite them for one polarization. We can excite with all different magnitudes, different phase. Example here, for example, is that these 3 elements are using single polarized excitation, whereas this one are using dual polarized. And if we look at the animation, we can see how the coupling, that there is a coupling that occurs between these elements. Furthermore, if we want to look at, for example, here the contour plot of beam steering, what we are seeing is the elevation and azimuth on the axis here, and we can do the beam steering. We can, for example, this beam steering, again, as I was saying, is just post-processing. There's no need for resimulate for different beam steering angles, just post-processing. So we can see here the beam steering. Fourth and last example is a 3D component array that consists of 24 times 12 dual polarized elements at 28 gigahertz. This means it has 576 excitations. This is quite a huge array already, and it includes the extended ground, it includes the radome, it includes the band, it includes 14,400 vias. Here is the antenna element, how it looks like. So it's again the cavity backpatch antenna element, but in this case we have 2 polarizations. This is a full wave analysis that includes adaptive meshing and frequency sweep. On a 48 core machine, it took less than 6 hours to simulate. So we can take this array analysis and continue. So we perform here an overnight statistical tolerance analysis. So we have again this 8x8 array, including the radome, including extended ground, as I have been showing you. This one includes over 3,000 vias. So we were running 243 design variations in less than 9 hours. So what we did was that we had 48 design variations simulated in parallel. And for each variation, we had 40 cores. And bear in mind that for each variation here, for each simulation we did, we were carrying out adaptive meshing and frequency sweep. And this is full wave simulations. And if we look here at the statistical antenna gain analysis, if we look at of the binning of the design variations, the left one shows the binning of the corner element. We are looking only at the bore side values, and in this one it says the total array gain. What we are looking again on bore side values. So when we go to larger structures, for example, when we're putting our antenna array into the casing could be quite large. In this case, we could still use full wave, but we could also do quick analysis using hybrid techniques. We could, for example, use shooting bouncing ray hybrid techniques here to quickly do fairly good estimation directly. Very good estimations on what is the properties of the radiation patterns when you put them inside the casing. How does it affect? So if we have a radiation, if we have a casing looking like this, and inside the casing we have this sort of structure, and inside here we will put our array. Let's say, okay, this is an example. So inside there we put the array, and we can see, okay, so first of all, we can start with the array in free space. How does it look like? And then we put the array inside this structure, which is inside this big radome unit or casing. Then we see what happens. This is the red curve. We see how this affects, right? And and we're using SBR plus here. And the next step is that we are activating the PTD, UTD. Basically, this is the physical theory of diffraction and uniform theory of diffraction, taking into account here the diffraction effects, and see what is the result of that. Another analysis, what we could do is that we can see how does it affect if we have smooth edges or sharp edges. The picture here clearly shows that if you have smooth edges, you will have lower side lobe levels compared to if you had sharp edges. So this is the sort of simulations that can be done to narrow down, the design space for optimization, and then could be carried out, for example, in HFSS completely to figure out the exact optimum design variation where you include the antenna array inside the casing as well. So to summarize, I've been showing how we could design the element antenna array. We looked at phase array synthesis using 3D components, how effective it is. This is full wave complex array examples, including adaptive meshing and frequency sweeps. Furthermore, we looked at this 243 design variations that was done in less than 9 hours. Actually, it was done in 8 hours, 42 minutes. This also includes adaptive meshing and frequency sweeps. We had a short look on how we could use hybrid techniques to do a study of when we put the antenna array inside the casing. Thank you for your attention.